Hey everybody. So this particular research paper is put out by a few different institutions, namely UC Berkeley, Princeton, as well as Carnegie Mellon University, and it's called Horizon Reduction Makes Reinforcement Learning Scalable. And then so what made all of these institutions come together for this particular research paper has to do with reinforcement learning and scalability. And so the best way to frame this is off the top, let's look at a typical learning curve for reinforcement learning, and we'll look at reinforcement learning loss. This is like this chart here from like this, just I typed in key learning reward loss but this is like very typical, right? And what you can see is that this went through like 250 epochs of training, and then the reward is just up and down, up and down. And then the total reward doesn't like fluctuate. It fluctuates a little bit, but it's never like increasing, right? There's never like a like you want to see like this, like on the right hand side, but you don't get this like the mean loss for reinforcement learning. Like this is a crazy one, right? The loss is actually increasing. It's typically like something like this, right? Or like what I showed you there. This is a typical example here too, where it's just like it's not it's not scaling essentially, and it's been a known thing with reinforcement learning overall. And then so it makes it kind of unique for reinforcement learning as a whole compared to other methods as to like why doesn't it scale overall. And then so in this research and in this work, the researchers prove that it can scale and it does scale. And it comes down to this concept of, they call it a horizon. And then so like within this, they give all of the code here in this GitHub repository called Horizon Reduction. And then you can link it directly from the research paper. And then they give like all of the code for all of their experiments, most of the data, right? So they like the data sets that they used for their largest tests were 1 billion size data sets. They give 100 million just because of the storage limits for GitHub. And then everything that you need here, right? And then they scaled this up to a 500 million parameter model, which they note within this. And then so they scaled it up to 500 million parameters and 1 billion rows of data. And that took 8 days of the training. And that's why they didn't scale it and couldn't scale it any higher. It's like, it's expensive to scale these things, like even to that level, right? 500 billion parameters, and 1 billion rows of data took 8 days of training, just 8 days straight of GPU. And like I'm sure that they didn't use a commercial, like they used a commercial GPU, I'm sure, a commercial grade GPU. And so this research paper in particular, they serve to answer the main question: to what extent can current offline reinforcement learning algorithms solve complex tasks simply by scaling up data and compute? So scaling, like how do they fix this problem overall, right? Like how do they get it to actually do better? And then so what we can see here with these these gray lines and like are the typical reinforcement learning, like these typical graphs that we're looking at, right? Especially like that first one where I showed you something like this, right? Very flat. And then here, like this one here, very flat, right? That blue line in particular is what we're looking at and what we would be comparing to. So the blue line is, and as opposed to the blue line, they actually get it to do stuff, to do something, right? And then so how do they do that? And then they utilize this method called horizon reduction. And then horizon reduction is straightforward as a concept overall, but they break it down into like essentially you take a problem and then you turn it and you take the policy and reduce it into simpler policy actions, right? And then so if it's like a huge problem, then it's like a huge horizon, right? Like too many steps to get to the problem. But that's what like a good analogy for horizon, right? How many steps does it take to get to the solution to the problem? And then so if it's like 30 steps, it's not, the model's going to struggle. It's not going to do it. If it's you give it like 5 different problems, and then each one of those has 5 to 4 different steps, it'll be a lot easier. Or 5 different steps, it'll be a lot easier for the model to go through and update and do what it needs to do, right? And then that's kind of what they prove out and go through within this and benchmark the improvement results within this. And so that's essentially like what their method is. They give a lot of like Q&A within this research paper, like how do you know that these tasks are solvable within the given data sets? Like how can you prove, or how do you know that they're solved? and able to be solved? Have you tried to further increase in the model size? That's where I went into, and I got that information from, that they only increased it to 591 million parameters. Are you sure this isn't just hyperparameter or design choice issue? They're like 99% sure. And then so that leads us to the cursive horizon. And then so they go through and then they set up their experiment here. And then here is where they break it out into two different types of horizons, right? So you have the policy horizon, so the cursive horizon and policy learning. And then you have also like for like the curse of the horizon and value learning as other value horizon reduction. So this one, policy and value. And so if you're familiar with like any sort of debate overall, policy and value, it always comes up, right? And so here you go. Algorithm number one deals with policy, and then algorithm number two deals with value, and that's pretty straightforward overall. As to the paper, what it does, right? So it's just proving that these scaling laws exist with regards towards reinforcement learning. And then they give algorithms and then like all of the code as to how to reduce the horizon. And so they're proving out that horizon reduction is, in fact, a method for making Q learning scalable. Then they give out like all of the code as to how to do it, and provide essentially everything that you need, all gift wrapped in a bow here, right? And then so again, this is to me very cutting edge, because this is a question that has been on the minds of researchers, right? Like when you look at Q learning overall, and you look at like what it does, like and you play around with it, and especially if you watch it, right? Like these rewards, like it doesn't seem like it's hard to understand how exactly it leads to like a performance increase until and how it actually works, right? Like, and how you would actually scale it up, because it's like random inputs like this, and so it's like even after like 200 epochs, right? You could have it like the model's performing like super well, and then all of a sudden just falls off a cliff here, like it as it does, right? And then it's just like okay, it's improving, and then just falls off a cliff, and it just like it doesn't really seem like it's like moving the bar that much overall, right? It's kind of the like big conclusion that you draw from it. It's hard to like pull the actual levers. Like, what are the actual levers that are within this? And then so like, I mean, I think like this is why again you have three of the biggest research institutions in the country coming together. Why are they talking about this? This is exactly why, right? Because it's no one can prove out these things, and then so they're the first ones to do it. It all comes down to horizon focus, which has been the topic of exploration more and more and more, right? This particular concept and their particular method has been coming up and talked about more and more in these research papers, which is essentially just taking this large problem and then reducing it into smaller problems. Like overall, we're all human. We all kind of learn the same way, and then so it all comes back to these same exact concepts that keep coming back up over and over again. And then so here we are again. In this instance, horizon reduction makes reinforcement learning scalable. I'll leave a link to this research paper, and then again from here you can easily link and access all of the code that they have and give you access to, and they fully open source MIT. And if you like this type of content, please like, subscribe. Thank you very much.